We'll now consider the system with 2 lag time constant and 1 lead time constant, and of course what you can do is compute the impulse response and the step response exactly, and this is what you obtain here. It is assumed that the 2 lag time constants are different. If they are not, well, you have to do a different type of partial fraction decomposition. Of course, those time domain responses are there for your information only. What is very important if you study this system, and this is true both in the time domain and the frequency domain, is that you should consider this system as, well, a process that is the succession of a lead lag system with lead time constant t lead and lag time constant t lag, right? So this is what we have studied just before, and then that this lead lag is followed by a first order system with, here the time constant is of course t lag 1, and it is followed, this lead lag, by a first order system with lag time constants t lag 2, right? And if you see this system with this transfer function like this, well, you can kind of recycle your knowledge that you have about the lead lag system with that you have of the first order system. This is especially true in the frequency domain, but you can kind of imagine the step responses of this one by considering that indeed it is the succession of a lead lag system followed by a first order system. What is far more interesting than computing the exact step response is to consider what is happening at the origin and to obtain the step response at the origin and information on the slope, and then look at the steady state behavior. And of course this is again using the initial and final value theorems specialized to the step response, and again this is considered in section 2. If these formulas here sound a bit strange, well, you should go and have a look in section 2. So for the step response, you can obtain the response at the origin by taking the transfer function and let s tend to infinity, and you can see here that it's 0. This is kind of normal. There is no feed through term over here because the relative degree is 1. It's the degree of the denominator 2 minus the degree of the numerator. So when you let s tend to infinity, you obtain a 0 and there is no direct feed through term. This is very different to the lead lag system, 1 lead time constant and 1 lag time constant, where because there you have a direct feed through kp t lead over t lag. If you have 2 lag time constants and 1 lead time constant, then the step response at the origin is 0. You can also compute the slope of the step response at the origin, and this is what you will obtain. Notice that if t lead is equal to t lag 2, this system is then a first order system, and you can see that you obtain kp over t lag 1, which is consistent with previous results. And of course the steady state behavior, since we're considering a unit step response, is that when t is tending to infinity, the step response will go to the steady state value of kp. Note that whenever the relative degree is 1, so that's the degree of the denominator minus the degree of the numerator, you will always have a step response at the origin that is 0 and a slope at the origin that is non-zero. Another example of a transfer function with a relative degree 1 is of course a first order system. We can now have a look at the step response of a system with 2 lag time constants and 1 lead time constant. So we'll consider 3 systems. They all have in common the 2 time constants, 3 seconds and 0.2 seconds, and the static gain is 1 in the 3 cases. The difference lies in the lead time constant. So we'll consider a t lead of 1, 9 and -1. And to kind of compute these step responses, we're going to consider an MV. As you can see here, we have a unit step at the input, and since we have 2 lag time constants and 1 lead time constant, you can view the overall system as, well, first a lead lag system, right, with gain 1, and then with constant at lead time constant t lead as +1, and we'll take the largest time constant here in the lead lag, right? So this is the lead lag system, and remember that the overall system can be seen as the succession of a lead lag with a first order system. This first order system will have gain 1 and time constant t lag 2, right? So here 0.2 seconds. So the transfer function is 1 over 0.2 s plus 1, and the output is, well, MV that goes through the succession of this lead lag and this first order system. So you have here the step response for these 3 cases in full line, but you can see also that we have the step response of the intermediate system, so the step response of the lead lag system in dashed lines, right? And we have been studying the step response of this lead lag system before, so you recognize the 3 step responses for the 3 cases. The lead is equal to 1, 9 and -1. To obtain the step response of the overall system, what you have to do is, well, kind of imagine the response of the output of the lead lag system to a first order system. Okay, let's take an example here with the lead is equal to 1, right? The output of the lead lag system and the step response of the lead lag system is here given in dashed lines. We have here a step response at the origin that is 1/3, right? And then a first order like type behavior, and the system settles at k, right, when t tends to infinity. When this signal is going through a first order system, you obtain the response here in green, and this is the step response of the overall system with 2 lag time constants and 1 lead time constant when t lead is equal to 1. We can see indeed that at the origin the step response is 0, and we have a slope, a non-zero slope at the origin, and this is because the overall system here has a relative degree of 1. You can see here that the slope at the origin, right, was kp t lead over t lag 1 and t lag 2. So for instance, if t lead becomes higher, you can see that the slope of course increases, and it changes sign when t lead is negative. Okay, so to obtain the step response of this system with 2 lag time constants and 1 lead time constant, well, you have to view things like this. You have to see it as the step response of the succession of a lead lag system followed by a first order system, and use the information that is given by the initial and final value theorems. So information, for instance, at the origin on the step response and its derivative. So here we obtain the frequency response of these same systems. So we'll proceed exactly as before. We'll have t lead s plus 1 over 3s plus 1. We have a gain of 1, and here we'll have this first order system with time constant 2s plus 1. We have been obtaining the frequency response for this system here previously, and here it will be shown in dashed lines, right? The frequency response of this first order system here is shown here in olive, and it has of course this first order behavior in 1, 2, 3, 4, 5. So here we have 5 radians per second. We have the cutoff frequency, and here you can see at the high frequencies this slope of minus 20 dB per decade. And here we have here the, well, phase shift. So at 1, 2, 3, 4, 5, here we have a phase shift of minus 45 degrees, right? So what you have to do to consider the frequency response of the overall system is to add both responses. So this will be given here in full line. Here we have the situation for t lead is equal to 1. So the frequency response of the lead lag system is shown here in dashed lines, right? And we can kind of see that this is correct because the high frequency gain is 1/3, so approximately minus 10 dB, and the frequency response of the combined system, well, you have to add the effect of the lead lag system with that of the first order system, and this is what you obtain, right? And since this transfer function here has a relative degree 1, it is normal to find this slope of minus 20 dBs per decade at the high frequencies, right? And similarly here, because the lead is positive, right, combining the phase shift, we obtain here a phase shift of minus 90 degrees. We can obtain the frequency response in the case where t lead is equal to 9. Again, we have to combine the response of the lead lag system. Here the response is shown in dashed line with the response of this first order system, and this is what you obtain here for the gain as a function of frequency. And again, at the high frequencies, because of this relative degree 1, we have a slope of minus 20 dBs per decade in the high frequencies. And if you combine the two responses, that of the lead lag in dashed and that of the first order system, you obtain here the overall phase shift for this system with 2 lag time constants and 1 lead time constant in the case where t lead is equal to 9 seconds. We can now have a look at the frequency response when t lead is equal to -1. The principle is still the same. We look at the frequency response of the lead lag system shown above and the response of the first order system, and then we add things, right? The difference here is that because of t lead is equal to -1, the phase curve that is associated to the lead lag system is that one over here, and we have at the high frequencies a phase shift of minus 180 degrees. So if we add the phase shift that is coming from the first order system, this will result in the high frequencies in a phase shift of minus 270 degrees. Here the overall frequency response is shown in full line in orange. For this case, the lead is equal to -1. Well, the next system is the second order oscillatory system. Transfer function with complex conjugate poles if zeta, here the damping ratio, is between 0 and 1, right? Omega n is the natural frequency, right? And the damped natural frequency is defined as follows. You can rewrite this transfer function as follows, and what is done over here is really to construct a sum of squares using these two first terms. So s plus zeta omega n squared, you'll have s squared plus 2 zeta omega n s, and then what you'll have too much is zeta square omega n square, and you'll have to kind of subtract it, right? So this transfer function, you can rewrite it like this, and as you can see, this is the Laplace transform of a damped sinusoid, right? Here we are using the translation in or the shifting in frequency, and in the inverse Laplace transform you'll have a term involving the exponential of minus sigma t. But what you can see here is that you have poles in minus sigma. Sigma here is zeta omega n plus minus the damped frequency. So if we compute the inverse Laplace transform, this is what you obtain: a impulse response that is, well, to have a sign you would need here at the numerator omega d. You don't have it, so you'll have a gain here omega n over omega d, right? Then you'll have this exponential of minus sigma t. This comes from this translation in the s domain by sigma, right? And then a sine of omega d t times u of t. Okay, so such a system has an oscillatory behavior, and the impulse response is a sine that is damped, and a system that has such a behavior is, for instance, a spring mass system with friction. In the previous slide we had considered a zeta between 0 and 1. If zeta is larger than 1, the system is overdamped and we have different real poles. These are these real poles, and then you can see this type of system as the succession of different first order systems in series, and we have considered that type of system before. If zeta is equal to 1, then the system is critically damped and we have a double real pole. So we have P of s is equal to omega n squared over s plus omega n squared, and if you take the inverse Laplace transform, this yields a, well, impulse response that is omega n squared t exponential of minus omega n t, right? So we have this special mode here because of the double real pole. We had already computed the impulse response of this second order oscillatory system, right? And we had rewritten the transfer function as follows, and you can see here that the impulse response is a sine at the frequency omega d, so the damped frequency that is damped by this exponential. And to find this, as I've said before, you need to use this property of translation in frequency, or this frequency shifting property, and here it is. So here you can see the impulse response of that type of system. The natural frequency is 1, right? Remember that the natural frequency is 2 pi over the natural period, right? So you can see it in for the undamped system that the period would be 2 pi over here, and you can kind of see indeed that when the zeta is decreasing, so when the damping is decreasing, well, you can see here that this sign takes more and more time to converge to 0, and you can see that when zeta is decreasing, you can start to recognize this natural undamped period. You can of course also obtain the step response of this second order oscillatory system. Well, you have to take the transfer function and multiply by 1 over s. This is what you obtain, right? And to compute the inverse Laplace transform, you need to perform a partial fraction expansion, and this is what you obtain. What you can see here in this term is the Laplace transform of a cosine that has been frequency shifted, right? And this is the Laplace transform of a sine that has been frequency shifted. So here is the time domain response, and as we had anticipated, you can clearly see here the cosine at the damped frequency that is damped by this exponential of minus sigma t, right? And you have a second term with a sine at this same damped frequency and also damped by this same exponential. So you'll have something that will be creating this envelope, right? This is this one over here, and then you'll have this oscillation in this envelope, and sigma here is really zeta omega n, so that's related to the real part of the poles of the transfer function, and omega d here is the damped frequency, so that's omega n times the square root of 1 minus zeta squared. So if zeta is becoming very small, then what you see here is approaching the natural frequency. So here is the associated step response for different values of the damping, and you can clearly see that this oscillation is damped by this exponential of minus sigma t. Sigma is zeta omega n, so you can see that when zeta is increasing, right, the damping is increasing as well. You should not be able to draw the step response of this type of system, but you should be able to recognize it. Notice also that when zeta is becoming small, you can recognize the natural frequency of the system and its associated period of 2 pi. Notice also that at the origin we have that the step response is 0 and the associated slope is also 0, and this is because the associated transfer function has a relative degree of 2. The degree of the denominator is 2 and the degree of the numerator is 0, and therefore if you look for the step response at what is happening at the origin, you will see that of course both the step response and its slope are 0, right? We had seen something similar for two successive first order systems, so a second order lag system. In process industry, very few processes are designed to behave like a second order oscillatory system. But the closed loop behavior, that is the process in closed loop with the controller, often a PID controller, will very often have this type of behavior. We will assume that what you see here is the closed loop step response. So the input here is a unit step on the set point, and the response given here in green is this unit step closed loop response. And usually with the controller, what will happen if you have done a good design, of course, is that PV will settle in such a way that PV corresponds to the set point. And since the set point here is a unit step, well, PV will settle to 1 over here, to a variation of 1. Well, very often the closed loop step response is used to characterize the performance of the controller, and the performance of this controller is characterized in terms of the rise time, the settling time, and the overshoot. Well, the rise time is defined as the time that is needed for PV to go from 10% of its steady state value to 90% of its steady state value. The settling time is the time that is needed for PV to settle in a band of plus minus 1% around the steady state value of PV. The overshoot is shown over here. It's the peak value of PV minus the steady state value, right? And very often this overshoot is expressed in percent, and we speak of percentage overshoot. So the overshoot is expressed as a percentage of the steady state value. Well, we can now have a look at the frequency behavior, and for that we use the transfer function, and we divide numerator and denominator by omega n squared, and this is what you obtain. So we can then use the usual trick. We consider small frequencies here, small with respect to the natural frequency. We replace s by j omega, and if you do this here at the denominator, the dominating term will be 1. So we'll have that the transfer function evaluated on the j omega axis is more or less 1. So this means that an input sinusoid will produce a very similar output signal, right? So the amplification is approximately 1 and the phase shift approximately 0 degrees. At high frequencies, much larger than the natural frequency, well, it is this term that will be dominating. Okay, if s is equal to j omega, well then s square is equal to minus omega square. So if this term here in the denominator is dominating, we can see that the transfer function evaluated on the j omega axis will be approximately minus the natural frequency squared divided by omega square. So there will be a decrease here in 1 of omega square, right? And there is a minus sign, so the phase shift at the high frequencies will tend to minus 180 degrees. This is a real number. The minus here will produce this minus 180 degrees, and this decrease in 1 over omega square will produce this slope of minus 40 dBs per decade. Well, we can now have a look at what happens at the natural frequency. So S will be equal to j omega n, right? And S square will be equal to minus the natural frequency squared, right? So at the natural frequency, this one will be minus 1. It will cancel out with this one, and well, The transfer function evaluated at the natural frequency is given by this expression that you can rewrite as follows. So we will see here that a sinusoidal signal at this natural frequency will be amplified by this factor 1 over 2 zeta. So a small damping factor will result in a high amplification, right? But whatever the zeta, you can see that the phase shift is minus 90 degrees. And this is indeed what we see. You can see here that at the low frequencies the gain is 1, so 0 dB, and the phase shift approximately 0 degrees. At the high frequencies, so high with respect to the natural frequency here, that is 10 radians per second, well, at the high frequencies we have a phase shift that is tending to minus 180 degrees, right? And well, the gain is decreasing here with a slope of minus 40 dBs per decade. At the natural frequency, so at 10 radians per second, you can see that the phase shift is indeed minus 90 degrees, and this holds for every zeta, but you can see that for a decreasing zeta here, well, you have a higher and higher amplification at this natural frequency. Let us do a little quiz. So you have to identify the step response of a second order lead lag, so 2 lag time constant and 1 lead time constant, and T lead is larger than T lag 1 and T lag 2. So I will show you the different possibilities, and at the end, well, you can push the pause button, use the rewind functions, and you have to try to identify the correct response. So push the pause button and use the reverse rewind functionalities to identify the correct response. We have here a system with a relative degree 1 as the denominator as degree 2, 2 lag time constants, and the numerator as degree 1. There is 1 lead time constant, and therefore using the initial value theorem you can see that this process has a step response that is 0 at the origin and a slope that is non-zero at the origin, and this is certainly consistent with A, right? It's also consistent with B, but here we have this damped oscillation, so we can exclude B. In C here we can exclude this response because we can see that there is a direct feed-through. The step response at the origin is non-zero. This corresponds to a lead-lag system, so 1 lead, 1 lag time constant. Here we can see that the slope at the origin here is 0, so this corresponds to a response of a second order lag system. And here again we can see that there is this damped oscillation, so we can exclude E as well. So we can see that the only response that is consistent with what is asked is response A. So the correct answer is A. Well, to give a word of explanation, we can see this second order lead lag system as a lead lag system. The lead S plus 1 over T lag 1 S plus 1, followed by a first order system with transfer function T lag 2 S 1 over T lag 2 S plus 1, right? So this is a first order system. This is here a lead lag system. And here we have the output, right? And we can kind of imagine the output of the lead lag system, and we'll show it here in dashed it would look something like that. It has a direct feed-through term, and it would look like something like that. And if this is the input now of a first order system, you can see that you will obtain this response. And as I've said, this is also consistent with this type of transfer function, because the step response must have at the origin a value of 0, which is the case, and the slope must be non-zero, and this is also the case. Let's do another quiz now in the frequency domain. So you have to identify the Bode diagram of a first order lead lag system. So one lead time constant and one lag time constant. So this is really a lead lag. The gain of the system is 10. The lead time constant is 1 and the lag time constant is 10 seconds. So I will show the different candidates, and then you can use the pause and rewind functions to find your answer. Well, using the parameters, we can see here that the low frequency gain, the static gain, is 10. So at the low frequencies we should have a gain of 20 dBs. The high frequency gain is non-zero here because we have a system with relative degree 0. There is a direct feed-through term, and this high frequency gain is Kp T lead over T lag, so it's 1, so 0 dB. We can see here that the lag action will start at 1 over T lag, so 0.1 radians per second, and the lead action will start at 1 over T lead. This is at 1 radian per second. We can exclude candidate A because the low frequency gain is not 20 dB. We have here Kp is equal to 10, so we should have 20 dBs. This is not the case. We have 20 dBs at the low frequencies for B, but the high frequency gain tends to 0, right? This is here a transfer function with a relative degree 1. You can see here that the phase will go to minus 90, right? And there is a drop here in the gain with a slope of minus 20 dB per decade. So we can exclude B. C seems to be consistent. We have here a low frequency gain of 20 dB. The high frequency gain is 0 dB, and the lag action is starting at 0.1 radians per second, and the lead action is starting at 1 radian per second. So this seems to be correct. Again, we can exclude this one here. At the high frequencies, the gain is tending to 0, and here again we have a problem because at the high frequencies here we have a gain that is minus 20 dB and we expect 0 dB. So we can see that the correct answer is C. This subsection deals with first principle modeling, so modeling using the equations of physics and data-driven modeling. The students in control engineering have separate courses on those topics. If interested, you can have a look at the slides or follow the associated courses that are available online. Very often, to design an internal model controller, a predictive PID, a Smith predictor, or to obtain a feed-forward law, we are satisfied with a good enough approximation of the process. And often this approximation involves a Broida model. A Broida model is a simple model with one time constant, a static gain of course, and a delay in the system. Right, so there are essentially two ways to arrive at this type of model. The first method is to obtain an open loop step response of the system, so you'll have to experiment on the system, and then you can obtain the gain, the time constant, and the dead time using graphical methods, and this is what we'll do in the control lab associated to this course. Another approach that might look unfamiliar is to use first principle modeling. So this is using the equations of physics to obtain a model of the system. Usually this model will be complex in the sense that you'll obtain a transfer function with a high degree denominator, right? So this transfer function will be too complex for the methods that are used in this course, and the idea is that you can obtain a simpler model using model reduction. Note that we use the notations t bar and theta bar because they are the best estimates of the time constant and the delay for this approximation of the process using the Broida model. In this slide we present another graphical approximation method that can be used to estimate the parameters for a first order system with delay, so a Broida model, right? So here we have obtained, using experimentation, a unit step response, in open loop, and this graphical approximation method, you'll be able to use it to identify an approximate model for lag time processes, okay, where you have a succession of several first order systems with also possibly a dead time. The gain Kp can be simply read by considering the steady state behavior. So you take the delta PV and you divide by the delta MV. Here we have a unit step response, so the delta MV is 1, and you can simply read the static gain from the steady state value of PV, right? So we are of course interested in the equivalent delay and the equivalent time constant. For that we have to look for the inflection point, right? The inflection point is the change in curvature, and the point where you have a change in the sign of the second derivative, right? Here you are, the function or the response is concave upward, and from here on it's concave downward. So here you have the inflection point and you can draw the tangent. It is not always easy to draw this tangent, as there might be some noise on the experiment that you have done, right? But once you have drawn the tangent, you can look for the times at which the tangent meets the steady state response, right? And the time at which this tangent meets the original PV, and it is now possible to obtain an equivalent delay and an equivalent time constant as shown here on the screen. Once you have obtained Kp and the equivalent dead time and time constant using this graphical method, you can obtain the approximated step response, right? And it is shown here in a sign. You could even see how good a job that you've done by considering at a certain time here the error, okay? And the estimation or approximation error will be PV at that time, so what comes out of the experiment, minus the approximated PV at that same time. So you can kind of compute the approximation cost as 1 over n, and here is the number of data points that you have collected times the sum of the errors squared, right? And this leads to the idea that what you could do is, well, try to minimize such a cost, okay? And this leads to an optimization problem where you minimize an identification cost that looks like that over kp t bar theta bar, right? And this will try to kind of minimize the discrepancy between what comes out of the model and what comes out of the experiment, right? And you can implement such an optimization using, for instance, fmin search, a MATLAB function. And this is something that you will do in the laboratory associated to this course. In this same laboratory, you will also experiment with other graphical approximation methods.